Hi all. So today we are going to discuss some examples and new topics in the third module. Okay. So we have already discussed about Hohmann transfer and done some problem, and this problem we have did in the class. And now this problem is mainly based on the transfer between circular orbits. Okay, transfer between circular orbits. That is, uh, we are having our main body, and there are circular orbits around this main body. There's one orbit, and there is another orbit. Okay, and we have to transfer in between these two orbits, so that we will design another parabola, or that is ellipse. Sorry, we will design an elliptical orbit that will able to transfer from our this orbit to, that is our inner orbit, inner circular orbit to outer circular orbit. So this transfer is called Hohmann transfer. Okay, this transfer, and we did some problems based on this kind of transfer. Okay, so uh, uh, now we are going to discuss another type of transfer in Hoffman transfer, that is transfer between two coplanar and coaxial elliptical orbit. Previous case we were discussing about circular orbital transfers, and now it is elliptical orbit. So just what is the main change is the formula only. Okay, so exactly as in the previous section, the transfer is performed in two stages via a transfer orbit. Okay, initially in the previous session, if we having a main body and the orbits are circular, and now the orbits are ellipse. So we can perform the same Hoffman transfer. We can use that elliptical transfer orbit to transfer from inner ellipse orbit to outer ellipse orbit. Okay, and this can also be used for transfer to the inner orbit also. If a satellite is in the outer orbit, then we can transfer the same satellite into the inner orbit also. Okay, the minimum energy transfer between the two orbits consists of delta v1, that is for from initial orbit at the perigee of orbit 1, and delta v2 at the apogee of the elliptical orbit. Okay, so here we have to add some delta v1 along with the this orbital velocity at perigee, and in order to move to a new transfer orbit, and when we reach at this point via transfer orbit, we can give another velocity, that is delta v2, in order to move into a new orbit. Or otherwise, if we don't add this one, then the satellite will continue in this transfer orbit only. Okay, so if we add this delta v2, satellite will find a new path, that is orbit O2. Okay, now for this transfer also we have to find some what semi-major axis of this transfer orbit. That is, our formula is like that. So this semi-major axis in circular orbit transfer, the formula was like uh, the average of the radius of two orbits. But here the orbit is elliptical, so we are not having a radius, that is fixed radius. So we will take the apogee, sorry, perigee radius of initial orbit, that is O1, and apogee radius of the next orbit, that is final orbit, and the average give the semi-major axis of transfer orbit. Okay, so there the formula was half into r1 plus r2. Here it is rp1 plus ra2. Okay, and the formula is again there is small difference, that is initially In that case, we have to transfer from what, circular to elliptical and elliptical to circular. That was the case. So the formula is like something. For circular orbit, our velocity equation is like mu by r. Okay, so one part here, the formula is for what, elliptical orbit. So these two are similar, looks similar. But in previous case, the formula is like this: delta v1 is equal to root 2 mu divided by r1 minus mu by a minus mu by r1. Okay, like this. Okay, you can check this. I will just move backward. So just look at this. This was the formula. Okay, ഞാനിപ്പോൾ പറഞ്ഞ പോലെ എന്താണ്, this for elliptical orbit, this transfer orbit velocity, and this circular orbit velocity. Then final velocity circle for the second transfer, that is transfer at this point. So this is the velocity, that is final velocity, circular velocity minus the transfer orbit elliptical velocity, this one. Okay, so ഇവിടെ സർക്കുലർ ആണെങ്കിൽ അവിടെ പകരം എലിപ്റ്റിക്കൽ ഓർബിറ്റ്. ഓക്കെ, ദാറ്റ്സ് ദ ഡിഫറൻസ്. So if you get the problems based on to circular orbit, that is you have to transfer in between two non-touching coplanar circular elliptical orbit, then you have to follow this formula. This just എന്താണ് ചേഞ്ച് ചെയ്യുന്നത്, ആ കൂടെ ചേഞ്ച് ചെയ്യുന്ന ഇവിടെ വെലോസിറ്റി മാത്രമേ ചേഞ്ച് ചെയ്യുന്നുള്ളൂ. ഓക്കെ, just velocity is changing. So you just study the formula for velocity. That is, this is the velocity for elliptical orbit. That is 2 mu by rp mu by a. Okay, at this perigee point. If it is apogee point, then it is ra. Okay, just see this rp ra. Okay. So our difference മാത്രം എന്ത് ചെയ്യുക, മനസ്സിലാക്കി വെച്ചിരിക്കുക. ബാക്കി എന്താണ് വെലോസിറ്റി കണ്ടുപിടിക്കുക, അതിൻ്റെ ഡിഫറൻസ്. ഓക്കെ, so next thing is, so this is about coplanar transfer. So we are not going to study more coplanar transfer. There are lots of transfer, but academic point of view നമുക്ക് Hohmann transfer and single impulse transfer നമ്മൾ ആദ്യം പഠിച്ച ഈ രണ്ട് കാര്യങ്ങൾ മതി. ആൻഡ് Hohmann transfer ബൈ എലിപ്റ്റിക്കൽ ട്രാൻസ്ഫർ ഒക്കെ ഉണ്ട്. സോ നമുക്ക് സമയം കിട്ടുവാണെങ്കിൽ അത് നോക്കാം. ഓക്കെ, anyway, we have transferred the satellite between orbits, or we have placed the satellite into orbit, and it is very essential to keep this satellite into the orbit for the operational time. Okay, so the maintaining the altitude of the low orbit satellite is the next topic. So for that, for low orbit satellite, the air density is high enough to produce a perturbing force, which in turns tends to decrease the orbit altitude. Okay, so the perturbing force acting in the acting along the satellite will cause the orbital decay of the satellite. Okay, so the satellite will move towards the Earth. The orbit will decrease during the motion. Okay, so there are many things such as weight, altitude, etc. Okay, the semi-major axis A tends to decrease owing to atmospheric drag. Okay, so the drag depends on atmospheric density conditions and on the satellite size, weight, and altitude, and can easily be estimated in advance. So these things can be estimated in advance. So based on the size, what will be the pressure, okay, what is the weight of the satellite, and like we can calculate. Okay, we can calculate the orbital decay in advance. So we can add some propellant, or we can keep some propellant in the satellite so that it can fire in order to raise that altitude to a previous height. Okay, so ഇപ്പോൾ പ്രൊപ്പലിൻ്റെ നമുക്ക് electric thrusters ഉണ്ട്. So there are lots of ways. Okay, so it is maintaining is important. Okay, the methods used is secondary. So in order to keep the altitude of circular orbit within prescribed limits, delta V maneuvers in the direction of satellite motion are executed when the altitude reaches the specified limit. So there will be some range in the orbital decay for the orbital decay. So if when it reaches the minimum limit or that maximum whatever it is that limit, so we will uh, achieve some delta v in order to raise to the normal orbit. Okay, in the preliminary stage of satellite technical definition and planning, it is important to estimate the mass of fuel necessary for this maneuvers. So ഇതാണ് ഞാൻ പറഞ്ഞ we should add some mass along with this satellite while launching. Okay, so that is mass means the propellant. Okay, a mass in terms of the propellant. So that propellant will be used for this orbital race, which is caused due to decay. Okay, so suppose that, so that estimation is like this. Suppose that an average disturbing force Fd is expected for a finite expected, then we can estimate Fd, that drag force, whatever it is. For time being, we will be considering the drag force. For example, drag force only. And for a finite increment delta V, the Newton's second law can be written as what was the second law? It's giving the force equation, that is F is equal to ma, that is delta v by t, where F is equal to Fd, that is force. Here the force is equal to drag force. Okay, now we can take this delta t to here. So Fd into delta t is equal to delta m propellant into g into isp. Okay, into g into isp. So there is some relation between this uh, what isp and delta v. Okay, so this specific impulse and delta v, there is some relation. We have already seen that. So this delta m propellant is the consumed propellant mass for the time interval delta t. Okay, time interval delta t with an assumed atmospheric drag of Fd. Okay, so this delta m is the weight of that propellant used. Okay, propellant used for the orbital transfer, that is for the impulse delta v for maintaining the altitude. Okay, so we can do an example for that. So the expected, there's an example. Okay, example. So the expected disturbance acting on a satellite located in a circular orbit of altitude 450 kilometers is 10 raised to minus 3 Newton. If specific impulse is 250 seconds, then how much fuel mass will be expended in 1 year? Okay, so we have to do the calculation for 1 year. Okay, so so we can draw this sample figure. So figures will be much more helpful. Okay. So assume that we are having a center of mass, okay, and we are having a circular orbit. Okay, we are having a circular orbit, and the orbit, this altitude is given, and what is the altitude? Altitude is 450 kilometers. So this 450 kilometer is the altitude, and so that what is the radius? Okay, sorry. So this radius is equal to here the earth radius is not given, so for standard we are taking it as 6376 78, sorry. So 6378 plus this 450. Okay, so this is the what our altitude. Okay, wait. For the time being, we are not needed to find this value. Okay, first we can write down this. It is given the altitude, uh, that is height is equal to 450 kilometer, and given ISP, ISP is equal to 250 seconds, and the force FD is equal to 10 raised to minus 3 Newton. And what else? And we know the gravity G is equal to 9.8 meter per second square. And we have the formula. Okay, then duration. Okay, duration in the sense. Okay, first we can write the formula. That is, we know FD into delta T. FD into delta T is equal to delta M propellant G into ISP. Okay, so this is our formula. So what are the needed quantities are FD. FD is there. Okay, FD is there. Delta T we have to find. Then delta M, actual quantity to be found is delta M G is known and ISP is known. So what is to be found? That is delta M propellant. Sorry, delta M propellant is equal to FD into delta T divided by this G into ISP. Okay. So what is FD? So FD is given, it is 10 raised to minus 3 into what is delta T? Delta T is the duration actually. Okay, it's the duration. It's for 1 year. Okay. So the ISPs are given in seconds and it is meter per second. So we have to convert the entire duration of 1 year into seconds. Okay, ഒരു വർഷത്തിന് മൊത്തം സെക്കൻഡ് എത്രയുണ്ടെന്ന് നമ്മൾ എഴുതണം. So we have 365 days into 24 hours into 3600 seconds. Okay, in 1 hour we will be having 3600 seconds, and like that we will be having 24 hours for 1 day, and for 1 year we will be having 365 days divided by, and this is the force 10 raised to minus 3, and divided by 9.8 into ISP is given, that is 250. And pause the video and do the calculation so that you will be getting it as yeah, 1287.18 into 10 raised to minus 2 is the value. So that is, you can say it is 12.87 kilogram. Okay, this is the mass, 12.87 kilogram of propellant that we need per year. Okay, per year. Actually, the unit is kilogram. The mass delta M used, M propellant is 12.87 kilogram, and per year we will be need this 12.87 kilogram. Okay, so here can not require the altitude data. Okay. So this is a kind of problem. So next, it is non-coplanar changes. So till now we have studied about planar changes and orbit, maintaining the orbit for a satellite, and now we are going to study the out of plane changes, that is non-coplanar transfers. Okay, so there are two kind of non-coplanar transfers. First one is simple plane change, and second one is combined plane change. Okay, simple plane change and combined plane change. Okay, so here look at this figure. So assume that this is our main body, and our satellite is orbiting initially in this orbit. Okay, it was here and it was orbiting in this orbit, and now we have to change its direction, or we have to change its orbit. Not we are not going to change the size of orbit, we are maintaining the size of orbit, but we are changing the inclination. So we have to change some theta angle. Okay, theta angle here. Assume that this delta I is equal to theta. Okay, so this kind of change. Okay, simple. നമ്മൾ ഓർബിറ്റിന്റെ സൈസ് മാറ്റാതെ we are changing the changing to a new inclination. Okay, new inclination. That is another plane. Plane inclination മാറുമ്പോൾ ഓർബിറ്റിന്റെ പ്ലെയിൻ എന്ത് ചെയ്യും? മാറും. Okay, so different inclinations ആണെങ്കിൽ different planes ആയിരിക്കും orbit. So initial plane നിന്ന് എന്ത് ചെയ്യുന്നു? We are moving to another plane. So what is the velocity required? So these are the two velocity vectors in order to in the two planes. So there will be a velocity difference. So that can be calculated using this formula. Delta V is equal to 2v1 sine theta by 2, where theta is the inclination. Okay, theta is the inclination. Okay. So this is the formula for simple impulse where the size of orbit is not changing. Okay, where the size of orbit is not changing, we can use this formula. Okay, a combined plane change alters the magnitude and direction of velocity vector simultaneously. That is, in combined plane change, we were changing. 1 second. Okay, so if we are trying to do this, that is combined plane change. That is, we are changing the magnitude, alters the magnitude and direction of velocity. Then it is what? Combined plane change, and this is the formula. Okay, and this is the formula. That is, we are transferring in between these two orbits. That is circular to circular. Example ഇതാണ്, circular to circular orbit ആണെങ്കിൽ the size is not changing. That is, the velocity vector will be same. Okay, velocity vector will be same for that orbit. So same circular to circular means same സൈസിലുള്ള circular to circular orbit or elliptical to elliptical orbit ആണ്. നമ്മുടെ inclination മാത്രമേ ചേഞ്ച് ചെയ്യുന്നുണ്ടെങ്കിൽ you can use this formula. Delta V is equal to 2v1 sin theta by 2. Okay, if we are changing the inclination between two non-similar orbits, that is circular to elliptical orbit. Okay, like that. Circular to elliptical orbit velocity എന്ത് ചെയ്യും? It will change. Okay, circular to another large circular orbit, അങ്ങനത്തെ കേസ് വരുമ്പോൾ the velocity will be changing, so that velocity and direction of velocity, or magnitude and direction of velocity, will be changing. So we can use this formula. That is, we will be using law of cosines. So delta V is equal to V1 plus V2 square, V1 square plus V2 square minus 2V1 V2 cos theta. So we will be discussing a huge example for this kind of motion for a better understanding. So ആ സമയത്ത് ഈ ഫോർമുലകൾ എവിടെ ഉപയോഗിക്കുമെന്ന് നമുക്ക് നോക്കാം. Okay, so this is for simple plane change and this is for combined plane change. So just look at an example where a satellite orbiting Earth in a circular orbit, altitude 200 km with inclination 28 degree, is to be transferred to a equilateral orbit of same altitude. Okay, what is the impulsive velocity to be added for the required plane change? Okay, that's our question. So from the question we can draw this figure or figures. So assume that we are having our main body. Okay, we are having our main body, and initially there is an orbit of about 200 kilometer. Okay, 200 kilometer ഒരു orbit ഉണ്ട്. Actually the main body is very small here. This is somewhat larger. This is our main body. Okay, and we are having an orbit with an inclination of 28 degree orbit. The altitude is 200 kilometer. Okay, so assume that this is our orbit. Okay, of 200 kilometer. That is, this much distance is 200 kilometer. Okay, this is 200 kilometer. Okay, and we have to change this uh, orientation to what a new orbit is transferred to a equilateral orbit. So equilateral orbit, in the sense, the inclination will be zero. For an equilateral orbit, inclination will be zero. Okay. So same സൈസിലുള്ള ഒരു equilateral orbit ലേക്ക് ഞാൻ മാറ്റുവാണ്. Okay, assume that this is the equilateral orbit. Okay. So inclination will be zero. So the difference in inclination is what? 28 degree. Okay. So this difference in inclination is 28 degree. Size is, again, it is 200 kilometer. Okay. Again, it is 200 kilometer. So both the orbit h is equal to 200 kilometers, so that the velocity will be same. So the magnitude of velocity is not changing, only the direction of velocity is changing. So we can use the simple transfer. Okay, simple plane change. So we can perform the simple plane change. And what is the formula for simple plane change? That is delta v is equal to 2v sine theta by 2. Okay, so here, what is theta? Theta is the this difference, that is theta is equal to 28 degree, and we have to find this v. So already we have h. So what is our r? We can find r. R is equal to 6378 plus 200. So it is 6578 kilometer is our r, and we can find this v using the formula v is equal to root of mu by r. For circular orbit, this is the formula for velocity, and this velocity is independent of mass, and both the orbit, the velocity will be same because both the orbits are of same altitude. So mu is v is equal to mu by r, that is root of mu is 4 into 10 raised to 14. It is not given mu, so we have to take this constant 4 into 10 raised to 14 approximate value, and this radius magnitude is 6578 into 10 raised to 3. So doing this, you will be getting the velocity as 7.8 kilometers per second. So do the calculation. So you will get 7.8 kilometer per second is the velocity. Okay. So now calculate, substitute this value in this equation, that is delta v, sorry, this delta v is equal to what? 2 into v. What is v? V here. 2 into 7.8 into sine 14 degree. Okay. Substitute the values. So for these values, the delta v change is 3.77 kilometer per second. So delta v required is 3.77 kilometer per second for this plane change. Okay, for this plane change. Okay, for plane change in impulsive velocity, add ചെയ്യേണ്ട impulsive velocity ആണ് ചോദിച്ചത്. So delta v is equal to 3.77 kilometer per second ആണ് നമ്മൾ ഇതിൻ്റെ കൂടെ ആഡ് ചെയ്യേണ്ട impulsive velocity, so that we can get a plane change of 28 degree. Okay, so it is simple impulse ആണ്. Okay, sorry, simple plane change ആണ്. That is, our altitude is same, so that the magnitude of velocity is not changing, only the direction is changing. Okay, so okay, I think you understand this question. Okay, മനസ്സിലായെന്ന് വിചാരിക്കുന്നു. നെക്സ്റ്റ് നമുക്ക് അടുത്ത് വരുന്നത്, there is a question about combined plane change, so we can discuss this the next video. Okay, so thank you.